This is the second in a series of videos in which I'm building a version of the Raiden RD6006 power supply, but rather than using an off-the-shelf cheap switch mode supply for the back end, I'm building a custom linear supply for it. The case is quite small with the Raiden that I bought, and so I needed to get a fairly beefy 360 watt power supply that would fit into the available space. So what I've opted to do is use two 225 VA transformers, and because I don't have any that are the right voltage, and while I could buy them, they are expensive, and also I thought it would make some interesting videos to show the process of rewinding the transformer. I've also been asked to show that anyway, so I thought that I would combine the request with making some interesting videos, and for the next two videos it will just be going through the process of rewinding the transformer. I will skip through a lot of it because obviously most of it's fairly tedious, but I'll go through all the important points. If there's anything I miss or anything you want me to show in more detail, then leave a comment. If this is something you've done many times, then obviously skip the videos and get back on track once we get to assembling the actual supply. Before we start this, I decided to start from basics. So if you haven't been through the process of winding a transformer and you're just interested in the general concept, then I thought I might as well include the basic steps. So in general, when you wind a transformer, you'll have two starting points. You'll either have a raw core with no wire on it, which is what I normally start with, or you'll have a transformer that has windings on it. If it's the first time you're winding a transformer of your own, then starting with a ready wound transformer is easier because it will give you some information. In the last video we looked at the turns per volt, for example, which you can't do if you don't have any windings on the transformer in the first place, of course. But there's other things as well that you need to know, and one of those is the number of turns required on the primary depending on your mains frequency, and that is something that's one of the most important calculations that you make when winding a transformer. It's not particularly difficult to calculate, but you do need to take several things into account when you do it. And for this transformer, because I know that the primary winding matches the core, although we're going to wind it to a different primary voltage, we do know the turns per volt required on the primary to get us fairly close to core saturation, and that's the key to getting a good transformer configuration. You need to try and approach core saturation because that's the way the energy is transferred between the cycles. So the way a transformer works, if you're not familiar, is we apply an AC signal to it, and in the first half phase of the AC signal you build up a magnetic flux within the core of the transformer, and that is used to store the energy that is then transferred to the secondary winding. And that's basically the way that you transfer energy. You do it through the magnetic flux that you build up within the core. So in order for the transformer to operate efficiently, you need to build a sufficient flux to make good use of the core. If you don't go high enough, then obviously you can't transfer as much energy. If you go too high, then you end up saturating the core. Now once the core saturates, so for example if the core saturates before the half mains cycle phase is complete, then the current in the winding will very rapidly increase, and you'll end up overheating the transformer and most likely burning it out. So it is a kind of a balancing act. You want to get fairly close to saturation. Bear in mind that mains voltage does vary quite a lot, and in one location it can vary, but also across the UK we have about a 20 volt variation from one location to another, and that does make it quite difficult to wind a transformer that will work reliably anywhere. But once you've got that worked out, then the rest of it is just a matter of mathematics, because it is a ratiometric device. Now, because it's ratiometric in terms of voltage and current, we need to take that into account when we rewind this. Now, of course, because the current is ratiometric and we intend to change this transformer from a 240 volt primary to a 120 volt primary, then we need to increase the thickness of the primary wire because the peak current will be higher. So I've worked out what it needs to be, and we'll be going from 0.6mm diameter up to 0.85. It might not seem like a big increase in the size of the wire, but it almost doubles the cross-sectional area, so that gives us much better current handling capacity. You don't need to go to quite double for a like-for-like change in the transformer winding, simply because the 120 volt winding will be a lot shorter than the 240 volt winding, and so its resistance will be less. And because the resistance is less at peak currents, it will drop less voltage, it will be more efficient, and so you can actually go with a slightly thinner wire than you would expect if you were doing a like-for-like swap out. In this case I'm using a slightly oversized wire, firstly because I have the space to do that, and secondly because that will give a more efficient transformer once it's finished. Okay, so there are many factors you need to build into winding a transformer. It's just really going through all the available information and making sure you're happy with the results. Now, if you're not particularly happy, what you can do is do what I'm doing here and just do a mock-up and a quick test. So I mentioned in the previous video this is an 18 volt secondary transformer, so we'll just test that. I've got it hooked up here to a rectifier and a capacitor just so we can do some testing. As I say, I know this transformer, so I don't need to do this really. I've done this before with this transformer, I know what its characteristics are, but just for clarity we'll go through and do this anyway. So I'll turn this on. We're looking at the AC voltage here. This is the raw voltage coming out of the transformer, and as you can see we're at about 18.3 volts. Now what we expect when we rectify and smooth this, which is what we're doing with the rectifier and capacitor of course, is if we multiply that voltage by 1.4, that will give us our rectified DC voltage. So if we take 18.3, multiply that by 1.4, then we get 25.6. Now if you recall from the previous video, I also said we need to subtract about 1.5 volts to allow for the voltage drop in the rectifier. That's a full load. With no load like this we're looking at probably 1.1, 1.2 volts, so I'll subtract 1.2 from this. So that gives us 24.4, so that's the voltage I would expect to see across the capacitor in this configuration. So I'll just turn it off. We'll hook this up to the capacitor. Switch to DC and I'll turn it back on. You can see the capacitor was actually already charged up still, but we're getting 24.6, which is fairly close to the 24.4. As I say, it will vary slightly depending on the particular rectifier and the load, and of course the voltage coming out of the transformer will drop under load because of the resistance of the primary and the secondary. But as long as we allow for that, then that'll be fine. You can calculate it if you know the resistance of the winding, because we know how long the winding will be, we know the diameter of the wire, so we can work out at a given temperature what the resistance of the winding will be. We then know what the voltage drop through it will be, and you can work all that out. It's quite easy to do. It's much easier with transformers like this that have relatively short windings, but when you get into smaller transformers that have thousands of very fine windings, it can be more difficult, because as the windings build up, then the length of each winding gets progressively longer, so it's much harder to estimate the winding length. But we know what we're aiming for here now is we want to wind the transformer with 300 turns on the primary and 60 turns on the secondary, and that will give us a 120 volt primary and a 24 volt secondary. Okay, so I'll get all this unhooked and then we'll look at the first step in rewinding this transformer. Okay, so if you haven't seen one of these before, it's a transformer winding machine or coil winding machine, CNC controlled, so I can program the number of turns that I want. It will wind at very high speed, I can use very small wire up to fairly large diameter wire, so typically I'll wind using wire like this, and the thickness of this is let's have a look, 0.04 millimeters. I can also use wire such as this, which is cotton wound, and this is for doing wave windings. So I have modified this machine to allow me to wave wind with it, and this makes very light work of winding coils. Unfortunately, I can't use this for the transformer we're going to make because it's a toroidal transformer, and this will not handle toroidal windings. If you're interested in how machines work that wind toroidal transformers, it's well worth looking into. They are fascinating machines to watch. Very big, very expensive. I don't have one, and so we're going to have to wind the transformer by hand, so it's going to be a much more tedious process than it would be if I could use this. If you do want to see this in action, I do wind a lot of transformers. I produce or rewind transformers for people that restore equipment, blocking transformers for TVs that have thousands and thousands of turns of very fine wire on them. And this makes fairly light work of it. But as I say, unfortunately I can't use it here, but if you do want to see this in action, then let me know and I'll produce a video the next time I rewind a transformer. So I'll get this out of the way and we'll look at starting the process of rewinding our power supply transformer. Okay, so we'll get started on the transformer. It's fairly rare these days that I wind one by hand, although when I was younger I used to literally wind hundreds of coils and transformers. In fact, I don't know if it'll come off on camera, but the muscle on this thumb is nearly 3 times the size of the one on this thumb, simply because when I was holding the coils it overdeveloped that muscle, so I do now have a very large muscle on this thumb. Just come in handy for this sort of thing, but as I say, I very rarely wind transformers by hand these days. Having said that, I would highly recommend doing it at least once if you're interested in electronics. You can learn an awful lot by doing this, and it is one of those subjects that the more you do it, the more you realise there's more to it than first meets the eye. So we'll start by removing the outer cover of the transformer. It's usually just taped on, so find the end of it. So in this case I reused a covering from another transformer when I did this. It's quite a long time since I wound this, it's probably 20 years or more. So we'll get this off. Okay, so I'll remove this and then we can start looking at the windings. Okay, so that's the outer cover off, and normally with transformers you'll find that the primary is on the outside. It's always a pain because normally if you want to rewind them you only really want to rewind the secondary, but you also have to take the primary off first, which is a bit of a pain, but that's the way they're wound, so that's what you need to do. So what I'll do now is take the primary off. It's just a matter of finding the starting end, unwinding it. Now I won't be reusing this wire, firstly because, as I said, it's too thin for what we'll need. If you were rewinding it to 240 you might want to consider reusing the wire, but it, generally speaking, isn't worth it. Once you've bent copper wire, it work hardens and it's very difficult to reuse it because you'll get kinks and it won't line up the way it came off and it'll look a mess. Also the winding will take up too much space. It's not too much of a problem on toroidal transformers, but for standard IE transformers or CT transformers, then you'll run out of space on the core if you're not careful. So I'll take this off. If it was a transformer you're trying to figure out the number of turns, then you should count the number of turns as you unwind them. Because I know how many turns I need, I'm simply going to cut these off. So what I'll do is, I could start with the end and wind it, but it's a very long and tedious process. So what I'm going to do is just cut through each winding, peel it back, take off the next one, and I can just go around and do that all the way around. and it will only take a few minutes then, but trying to pull the wire through repeatedly will take a long time. So I'll do that. I'll get the primary off, and then we'll get back and look at taking the secondaries off. Okay, so I've cut all the primary turns. It took about 5 minutes, so it doesn't take too long. Just had to remove a few bits of tape. And what I can now do, of course, is just pull these out through the core. It's much quicker and easier than trying to unwind the turns, because you'd have to pull each one through the entire length of the wire. These can just be easily pulled through. I'll just get all these out of the way. Okay, so I have all the primary turns removed. If you've never done this, one thing that will most likely surprise you is just how big a pile of wire you end up when you unwind a transformer. And now we've got to this stage, of course we should have 600 of these. If you want to just double check everything, if you're not 100% certain as to the number of turns you had on your transformer, what you can do, of course, is just count these and see if you have the number that you expect. Or if you're lucky and you have a counting scale, so something like this, then you can actually use the scale and count the number of turns. It won't be 100% precise because they won't all be the same length, but it'll give you a good average and a good idea as to roughly how many windings there were on the transformer. So I'll just do that now. I'll put the windings on the scale. We'll do a quick count and see if that meets what we expected, which was 600. Okay, so I've got the scale set up with 25 of the windings, and this will give me a rough average for the different lengths and should give us a fairly accurate count of the total. What I'll do now is dump the rest in, and it should give us something fairly close to 600. And there we go, exactly 600. So we can be fairly certain that our calculation was fairly close, and that there were indeed 600 turns on this transformer. So we can now move on and look at getting the remaining windings off. Okay, so it's just a repetition of what we've just completed, removing the outer cover and then unwinding the windings themselves, or just cutting them off. Again, I won't be reusing the wire on the secondaries. I'll just cut it off and we'll use new wire. It'll be a lot easier on the new winding. You can see here that there are actually 4 windings on this transformer, and what I will do is as I unwind these, I'll show you as I take each one off, and you can see how they're arranged. One other thing that's worth looking at here, and I'll look at this more closely when I take this outer cover off, is if you've ever looked at toroidal transformers, you'll notice that even the professionally wound ones look very untidy in terms of their windings compared to the standard type transformers, and that's mainly because when you're winding these, there's no way to lay down the windings so that they're parallel to each other. So in other words, you can't lay them alongside each other, simply because the distance around the inner part of the winding is not the same as the distance around the outer part. So even if the windings are snugly up against each other in the middle, they'll be splayed out and spread at the outside, and then when you put the next layer on, it obviously makes it very difficult to get a neat winding, a neat layer on there. Not normally too bad with larger transformers like this, because there aren't that many turns on it, and of course we'll be putting back even fewer than are on here. So we'll be putting back probably a quarter of the number of turns that we had on the secondaries, and only half the number on the primary. So I'll get this outer cover taken off, and then we'll look at the windings a bit more closely, and you'll see what I mean about them not being particularly neat. So if you were going to reuse the copper, you'd have to be fairly careful not to damage it. I'm not going to reuse the copper, so I can take a shortcut. So you just get a knife, run it round, and what you can then do is just peel this cover back, and it will come off a bit like the windings did on the primary, and it will only take a few seconds then to get the entire thing off. Otherwise what you end up doing is just pulling it continually through the core, and it does take forever to get it off, but this will just take a minute or so using this method. So that's the cover removed, and you can see what I meant about the windings not being close on the outside. They're very close together on the inside, but not on the outside, and you can see that the way they are fairly untidy in the way that they overlap. one thing when you're winding these transformers, there's several ways you can go about it, and the professional transformer winding companies, even if they're putting down a winding with just a few turns on it, they will tend to spread that winding right round the core. So you can see this thinner winding, which is the 12 volt winding, goes right round the core, even though it could have just occupied a fairly small space. Now I did that simply because it's the better way of winding transformers. It will give you a better result, and you'll get a much better performance from the transformer. And of course it also evens out the windings on the core. So you don't need to worry about removing all this tape. This is just here to hold these windings in place and to give a cleaner top winding, because if you don't put this in place then the top winding becomes very untidy very quickly. But don't worry about removing that. This is just normal transformer tape. All you got to do is get the end free, and then you can start unwinding it, and this tape will just come off. If, like me, you're not intending to reuse the copper, then you can again just cut these off, and it's a much quicker way of removing them. We don't need to worry about the number of turns on here anymore. We've checked the primary, so we know what the ratio for the transformer is. We know how many primary turns to put back on, and that will tell us how many secondary turns that we need. So I'll get this cut, and we'll get it peeled off, and that should leave us with just the core. Okay, so I've removed the 12 volt windings. They were on top. Now when you wind transformers, especially toroidal transformers, if you want a balanced pair of windings, say plus or minus 18 volts, it is important that you wind them like this as a pair of windings. Don't wind one and then wind the next on top. Because of the way that toroidal transformer windings lay down, you'd end up with the second winding significantly longer than the first in terms of the copper that you're putting onto the core, and that means that you would end up with a differential voltage coming out of them under load. So all you do is you just wind them as a pair, so just wind them both at the same time. It's generally fairly easy with windings like this because there aren't that many turns. There's only 36 turns, for example, on the 18 volt windings. So if you wind them as a pair, then you're just winding two wires 36 times around the core, which is quite easy to do. Also, as I said, once you've bent the wire, it's very difficult to get it straight again because it work hardens, so there's not really any point trying to reuse the copper for this. The best thing to do is cut it off and recycle it as copper. I did used to reuse copper wire when I took it off transformers, but it's very tedious. You end up with quite a messy looking transformer, and it takes far longer to rewind it, so I don't do that anymore. You can do that if you want to save a bit of money, but copper wire is a lot cheaper now than it used to be, so I don't bother. Also, there's not that much in terms of length of copper wire on this transformer. So the way I get this off is just one wind at a time. Loosen the winding off, cut it, feed it through, cut off the next one, and then you just keep going round. It's very quick and easy, and it will only take a few minutes to get the entire winding off. Okay, so we then have the winding completely removed from the transformer. We can take the caps off. This one's stuck on there. Okay, I'll take that off later. They do tend to get stuck on here over time. And you can see this is not actually a ferrite core, this is a wound iron core. Now someone did ask me whether I would be comparing different core types for this, but no, I won't do that. If it's a commercial product, then you do need to take into account the core material you're using. It's not particularly important for a project like this, but if it's a high frequency switching power supply, that sort of thing, then the core material is very important. It's not really important for this. This is not quite as efficient as a modern ferrite material, but we're only talking about a % or so of losses at full power, so we don't really need to be too concerned about that. As I say, a wound iron core is perfectly adequate, and that's what we'll be using, of course, for this project. This is an identical wound core to the other transformer, so I've done the first one. I've got another one of these to do. But as you've seen, it's very quick and easy to get to this stage. It's taken about 15 minutes in total to prepare this core, and it'll take about the same to do the other one, probably less because I won't have the camera in the way, and then we can start rewinding. Unfortunately, rewinding takes a lot longer than dismantling, but we'll look at that in the next video. In the meantime, if there's anything else you want me to cover or go over in more detail, then please let me know. But as you can see, it's a relatively straightforward process. It's just a bit tedious and a bit messy, and you end up with a nice collection of copper wire that you can recycle. So off this, there's about ½ kilo of copper on this one, and some of the bigger transformers you'll get several kilos off. But the main thing, as I said, is to make sure that you understand what core you're using and what is going to be required in terms of the number of windings and their thickness when you come to rewind. Okay, so in the next video we'll look at putting some copper back onto this core.